So notice this curve doesn't look like it's going to quite reach 0 over here. Okay? Well, if strong acids reach 0 or below, or appear that they're going to reach 0 or below, then what does that tell you about what this acid is going to be? It's going to be weak. So we know this is a weak acid. How many cliff faces do we have? We just have one. I know this might fool you a little bit, but this initial sort of hill here is not really a cliff face. Okay? And that's an interpretation matter. You have to be able to figure that out. Okay? This is not a cliff face. This one is. Okay? So our equivalence point is going to be right here. The equivalence point is identified by where it comes out on this line. The volume of base is right here. We can still calculate the concentration of the acid based on the amount of base used. Okay, it's a weak acid. Alright, so based on the amount of amount of base added, we can determine all those things we need to determine. Okay? And if we only have one equivalence point, what else do we know about the acid? Besides the fact that it's weak. If you've only got one equivalence point, what else? Monoprotic. It must be a monoprotic acid because there's only one equivalence point. So monoprotic acid only has one hydrogen that can be removed. One hydrogen, a proton that can be removed. That's why it's called, only one proton can be removed. That's why it's called monoprotic. One proton can be removed. Okay? Weak monoprotic acid might be HF. Or, we've already done a lab with one weak monoprotic acid. HCH3 CO2. That's a weak monoprotic acid. If we put the HF with KOH, the one hydrogen gets pulled off and joined up with the hydroxide, and you get water. The potassium and the fluorines are freed. Or fluorides. Okay? And we've already done all this for acetic acid. We did that Tuesday and Wednesday. Okay? We looked at the same sort of stuff for those. Okay? But at this equivalence point, the number of hydrogen ions removed from the acid and the number of hydroxide ions in solution are going to be equal. And we can calculate stoichiometrically from the amount of this stuff to the amount of this stuff and find the concentration of the acid. Okay? Huh? Y'all got all that? Okay, let's look at another one. One 1001. For those of you listening to the video, somebody asked me to go back for 1 second, so I was just kind of being playful there. Some students get a little upset about that, but this particular student's pretty good about that sort of stuff. So, all right, now. There you go. Boy, you're just on fire today, huh? 3 equivalence points. Triprotic. Got an equivalence point here, here, and here. The concentration of the original acid can be determined from any one of these three. You want to choose the one that seems to give you the clearest indication. Okay? So the first equivalence point, let's use this as our example here. This is called phosphorus acid. You should be able to name these. One hydrogen comes off. That means we're going to have H2PO3. Okay. That one hydrogen coming off joins up with the HOH, so that gives us water. And then we have a potassium, at least in this representation, we're going to have one potassium freeze. We can show it in different ways. Now, if I remove one hydrogen here, that means that this species has to have one more thing to be complete. What else do I have to put on this to be complete? I removed one hydrogen here from a neutral compound. What does that make this compound? If I remove one hydrogen, single negative. Okay? So that's the first deprotonization. We removed one proton. That's the first deprotonization. Okay? And there are two more hydrogens now that can be removed from this. And each one of these has to have a separate equation. Alright? Each one of these has to have a separate equation. The second equation starts with this species here. We're adding base to the solution as we go about titrating the acid here, which will show up on this graph. I pull one hydrogen off, so I'm going to have HPO3. If I have a one negative charge here and I pull one proton off, what charge does this species have? 2 negative, you're right. Okay. And then this hydrogen, a proton, goes over here and joins up with the hydroxide part of this formula. And we get water. Good. That's good. It's good when you speak up like that because you're becoming an active learner. Active learners learn more.
I can't be an active learner when I'm writing so much.
Wrong answer. You can be an active learner. It's just maybe a little bit harder. What?
I want to refer back to the graph, but this is the same thing as it last. Would this be a weak probably?
This is a weak. Very good. All right, boy, you're really on fire today, aren't you? I mean it. This is a weak acid.
You're like literally on fire today.
This is a weak acid right here because it doesn't appear to be going low enough to give us an indication we would be down at a pH of 0 or below. Okay? And it's tripodic because we have 3 equivalence points. Okay? So this is the second deprotonization, and there's one more deprotonization. I'm going to let you guys do that now. I want you all be active learners by predicting what the next equation is going to look like based on everything you've learned so far. Based on these two examples here, one more proton to pull off, show me what it's going to look like. I'm not entertaining.